Quantitative descriptions of matter. As we've seen previously, chemistry is the study of matter, and matter is essentially all of the stuff or all the material that's around us. When scientists describe matter, they use one of two types of descriptions. We discussed this previously when I gave the example of a patient that provides a urine specimen or a urine sample. One way that you could make observations of that urine sample is to give what are called qualitative descriptions. A qualitative description simply uses words to describe the qualities of the sample or of that matter. Examples of qualitative descriptions for this urine sample would include things like the fact that it's a liquid or that it appears to be yellow in color. You could describe it by saying it appears translucent, meaning you can see through it, or you could get adventurous and note that it's odorless. In each case, these are qualitative descriptions because they simply use words to describe the qualities of the sample. What we'll focus on today are what are called quantitative descriptions. These quantitative descriptions are ways that we quantify or measure the characteristics of matter. In the case of the urine sample, there's a lot of different ways it could be quantified, but you might do things like measure the mass of the sample and determine it's 45 grams. You could measure the volume of the sample. Perhaps you determine it's 41 milliliters. You could measure the density or the temperature of the sample. In these examples, notice that we use measurements to quantify the information about that matter. When using measurements or quantitative descriptions, we're virtually always going to measure numbers in order to get information about the matter we're discussing. Regardless of whether we're in a research setting, a medical setting, or just using measurements in our day-to-day life, you'll notice that all measurements always have two parts. We use the example of a urine sample and notice that you could measure the mass of it and determine that it's 45 grams. But in a much less technical setting, maybe somebody asks you how long you need to put something in the oven to cook, and you say 15 minutes. These are both measurements, and notice that both of them have two parts. The first part is the number. This is the information that gives us a magnitude or a value to the information that we're seeking. The second part of a measurement is always a unit or a label. And it's important to realize that whether we're dealing with a casual measurement or a very technical one in a laboratory setting, all measurements must have both a number and a unit for them to have meaning. For instance, if someone weighed a urine sample and you asked them how much it weighed and they said 45, you don't know whether they mean 45 grams, 45 ounces, or 45 pounds. So it's important that all of our quantitative descriptions, or all of our measurements, always have both a number and a unit or a label. What we'll focus on first are the units, and then later on we'll come back and look at how we write numbers scientifically. If you were born and raised in the United States, or if you've been here for any length of time, you're probably very comfortable working with units in the United States standard system of measurement. U.S. standard units have actually evolved over time from a number of different systems, and these are the units that you're probably very comfortable working with. In fact, they're probably the ones you go to when you want to give information. For instance, if you're measuring length in the United States standard system, you might measure that length of an object in inches, or if it's longer, perhaps in feet or yards. If we're talking about a very long length or a distance, we might measure something in miles. Meanwhile, if you want to measure something's mass, in the United States standard system you have a variety of units you could use, things like ounces, pounds, or maybe tons if it's something that has a very large mass. With volume, again, we see that there's many units. You can measure the volume of a liquid in fluid ounces, pints, quarts, gallons, as well as many other units. And in fact, herein lies one of the biggest disadvantages to the United States standard system of measurement. It's that there are so many units. There's a lot of times where it's up to you to decide which unit to use, and you may not reach the same conclusion about the most appropriate unit than someone around you. If you've ever baked something or cooked in a kitchen, you know that sometimes what you're thinking of in terms of ounces might be different from what something in a recipe is given. Perhaps it's in tablespoons, or perhaps it's in gallons. So one of the disadvantages to the United States standard system is that there are so many units that are involved. The other disadvantage is there are so many different numeric relationships between these units. And these numeric relationships are the sort of things that you've had to memorize and get used to using over time as you were exposed to this system. For instance, think about the different units of length. You probably know off the top of your head that the relationship between inches and feet is that there's 12 inches in 1 foot. You know that because you had to memorize it at some point in your life, and you keep it in your mind as part of your working knowledge. If you need to change between feet and yards, you have to remember that there's 3 feet in 1 yard. And if you have to change between inches and yards, now you either have to memorize, look up, or calculate that there's 36 inches in a yard. When you move on to miles, there's even more numbers that you have to memorize. Do you know how many feet are in a mile? Do you know how many inches or how many yards are in a mile? In fact, even those of us that are very comfortable with this standard system usually don't know all the numeric relationships. This is a frustrating system to work with when you need to convert between different units, and this is one of the reasons that it's not the chosen system of measurement in most of the world, nor in scientific laboratories. In fact, if you go around the world, there are only 3 countries that use the United States standard system of measurement. It's the United States, Liberia in Africa, and the country of Myanmar, better known as Burma. Other countries sometimes are comfortable using standard systems, but the majority of other countries around the world in all scientific settings use the different system of units, and that is, of course, the metric system. Now, the metric system is used throughout the world, and as you'll get comfortable with, it's used in all scientific, technical, and medical settings. The reason for this isn't to make life harder on people who didn't grow up with it. It's that it's actually a remarkably simple system of measurement. In this day and age, as you already know, most of our science crosses international boundaries. You may take a medication that was researched in Germany, produced somewhere in South America, and then went through patent testing in Japan. So it's important that everybody's able to work with each other, especially because patients, medications, and technologies cross so many international boundaries. The biggest advantage to the metric system is that it's a very simple system of measurements. It eliminates all of those units that are used in the United States standard system and replaces them with just one base unit for every type of measurement. So no longer when you're presented with measurements of length do you need to remember inches, feet, yards, miles, and so forth. There'll just be one simple unit that you can use every time. To help adjust for very large and very small measurements, that one base unit can be adjusted using a prefix to change its magnitude. So the simplicity of the metric system comes from the fact that it uses base units with a simple prefix to change the magnitude. Let's look at an example of how the metric system makes things simple. If you wanted to measure the length of a football field, if you use the United States standard system, you might know off the top of your head that most football fields are 100 yards in length. How many feet is that? Well, at a relationship of 3 feet to a yard, that means there's 300 feet. If you want to know how many inches that is, you're probably going to have to write it down or get a calculator out to do that calculation. In the metric system, we'd likely measure the length of a football field in a unit called meters. A meter, we'll see later, is roughly almost the same size as a yard. So in fact, a football field is about 91 meters long. Now, if I wanted to measure something much longer or that had a much greater distance than one end of a football field to another, for instance, something like a road trip, I wouldn't have to change to an entirely new unit. I would just adjust that unit of meters by applying a prefix. A very common one to apply is the prefix kilo, which gives us the term kilometers or kilometers. In this way, it simplifies the fact that you don't have to decide between different units. You simply use the only base unit that's appropriate, and then you can adjust it as you desire using a prefix. Let's look at a specific example of how the metric system works numerically. We'll learn later about the wide range of prefixes in the metric system, but for now let's just focus on this one very simple example. The example of having a base unit called the meter. Now I mentioned previously a football field in the United States is about 91 meters from one end to the other. So that's a reasonable number. If someone asked how many meters and you said 91, that sounds reasonable. It's not a very, very large number and it's not a very, very small number. If we were to measure something longer, such as the distance of a road trip, we could still measure in meters, but depending on the length of that road trip, we might end up with a number that's large enough to make it less convenient. For example, the distance from Spokane to Seattle is approximately 451,000 meters. Now in this case, I'm using the lowercase m, which is the official abbreviation for the meter. It's important to learn these abbreviations and pay close attention to when they're capitalized and when they're lowercase, because that has significant meaning in the metric system. So it's okay to report the distance from Spokane to Seattle as being 451,000 meters, but because that number is large, you might choose to use a prefix to simplify the number. If we're dealing with numbers that are much larger and that make us want to simplify the number, we'll look at the numbers that fall higher on this arrow than the base unit. For instance, we already said that there is a prefix called kilo, which is represented with a lowercase k. What kilo means is that you're dealing with something that is 1,000 times larger than the base unit. In the case of a kilometer, we're dealing with the fact that a kilometer is 1,000 times bigger than a meter. I'm abbreviating the number 1,000 using 10 raised to the exponent 3. That really just means a 1 with 3 zeros behind it, or the number 1,000. You can write it either way depending on what you're most comfortable with. Because of this fact, I can simplify that number, 451,000 meters, by adjusting it by a value of 1,000. In any case where you're dealing with numbers larger than the base unit or larger than your initial value, we can always divide by the value of the prefix. In this case, divide by 1,000. So one way to change meters to kilometers is to take 451,000 and divide it by 1,000. This will give me the answer that there's 451 kilometers, or 451 kilometers, in the distance between Spokane and Seattle. That's one way to do it. Another way to do it is simply to move the decimal point. Anytime you deal with a value that's larger, we always move the decimal point to the left. In this case, the number 451,000 has an implied decimal point at the end of the number. If I want to move it by 1,000, that's 1 with 3 zeros, so I'll change it by 3 spaces. Again, 1, 2, and 3, and that gives me the answer that I have 451 kilometers in that same distance. So whether you choose to divide or multiply, and whether you choose to move the decimal point, you can arrive at the same conclusion. Let's practice this by going in the other direction. If my football field is 91 meters long, how many kilometers is that? So 91 meters, when I think about that value, if I change it to kilometers, again a kilometer is much larger, so my value is actually going to get smaller. This is much like when you say there's 12 inches in 1 foot, you need many of the smaller unit, the 12 inches, to equal 1 of the larger unit. In the case of a football field that's 91 meters long, I know that if I change this to kilometers, my value will change by an order of 1,000. Again, you can take 91 and divide it by 1,000, or you can take 91 and move the decimal point. In either case, whether you choose to move the decimal point by 3 positions, or whether you choose to divide by 1,000, you'll discover that there are 0.091 kilometers in the length of a football field. Now, while there are many units that are larger than the base unit in the metric system, there's also units that are smaller. Very commonly in science these days, we're working with smaller and smaller quantities and smaller units. So you're likely to run into more of the units that are smaller than the base unit. Let's look at just one to start out. If you go to a value that is 100 times smaller than the base unit, you'll end up using the prefix centi. And centi should remind you of century because it represents something 100 times smaller. So in this case of using meters, if I go 100 times smaller than a meter, I'll be dealing with 100 centimeters. That means that I can convert meters to centimeters, I can convert centimeters to meters, and I can also convert centimeters to kilometers and vice versa. The important thing to realize is they're different by orders of magnitudes that are essentially just adding or removing zeros from the value. For instance, 91 meters would be 100 times bigger than the centimeters that are used to measure it. So in this case, if I'm dealing with something that's smaller, I'm always going to move the decimal point to the right, or I'm always going to multiply by the value. If I wanted to change 91 meters to centimeters, because there's more centimeters in a meter, or because it's smaller, I'm going to multiply. I'm going to multiply by the value 100, or move the decimal point 2 values to the right to discover that there's 9100 centimeters in a meter. So again, with the metric system, you may have some familiarity with it from before, and this might be review, but it also might be something that's new to you. And in any case, just remember that the more you practice with these, the easier they'll become. In the end, one of the things that makes the metric system so simple is that you can apply the same prefixes to every different type of unit measurement that's out there. So in the United States standard system, you would have to learn one set of conversions for length, one set of conversions for mass, another for volume, and so on. The nice thing is the metric system prefixes stay the same. So whether you're measuring length in meters or whether you're measuring mass or volume in other units, which we'll talk about momentarily, you're going to use the same prefixes. Let's look at some of those base units now. There's a variety of different metric base units, and it's important to know what they're used to measure as well as how to correctly abbreviate them when labeling your values. We've just discussed that the metric unit for length is the meter, which is abbreviated with a lowercase m. So I can have centimeters, meters, kilometers, or as we'll see in a few minutes, a variety of other prefixes attached to the meter as a base unit. If you're measuring the mass or the weight of something, you'll measure in terms of grams, which is represented with a lowercase g. That means you can have grams, you could have centigrams if you're measuring something smaller, or maybe you'd use kilograms if measuring something larger. For volume, we use the base unit of a liter. And liter is actually one of the few things that's represented with a capital letter in the metric system. The capital L means liter. So you could measure a centiliter, a kiloliter, or a liter, as well as the other prefixes we'll get to in a minute. For energy, we'll run into a unit called the joule with an uppercase J. And for temperature, in a few minutes we'll be talking about Kelvin, which is a temperature measurement represented by the letter K. Now, these base units are going to be some familiar to you and others not, but you'll get more comfortable with them as we get to use them throughout the length of this course. Let's look now at some of the other prefixes in the metric system. We've already discussed kilo and centi. A kilo is 1,000 times larger than the base unit, meaning you always move decimal points to the left, or you always divide by the number, divide by 1,000 in this case. And centi is smaller than the base unit, so you will always move your decimal point to the right, or you'll always multiply by the value, 100 in this case. Let's look at some of the other smaller prefixes. You might have heard of deci before, and deci should make you think of decimal or decade, and that's because this is 10 times smaller than the base unit. So in other words, you can change your base unit into the prefix deci simply by moving your decimal point one place or multiplying by 10. That means you could have a decimeter, a decigram, a deciliter, and so on depending on the circumstances. Smaller than deci and centi is the milli. It's important not to confuse milli with the word million. Milli, which is represented with a lowercase m, represents 1,000 times smaller than the base unit. So notice that milli means 1,000 times smaller than the base unit, whereas kilo is 1,000 times larger than the base unit. Also on the smaller scale, we tend to jump down to values that change by three orders of magnitude. In other words, 3 zeros. So a milli is 1,000 times smaller than a base unit. The next prefix that's commonly used in the metric system is micro, which is represented with a Greek letter called mu. It really just looks like a cursive U with a little tail on the front of it. A micro is 1,000,000 times smaller than the base unit. That means that a microgram is 1,000,000 times smaller than 1 gram, or a micrometer is 1,000,000 times smaller than a meter. Still smaller than micro is nano, which you've probably heard of in terms of nanotechnology. Nano is 1,000,000,000 times smaller than the base unit, or 1 with 9 zeros behind it, and it's represented with a lowercase n. And finally, even though the metric system goes further, one prefix that we're starting to use more and more in science is pico with a lowercase p, which is 1,000,000,000,000 times smaller than the base unit, or 1 with 12 zeros after it. On the larger end of the scale, we've already discussed kilo, and there's a couple other ones that you'll see getting tossed around, although not quite as commonly as deci, centi, milli, micro, nano, and pico. On the larger end of the scale, you might run into hecto, which is 100 times larger than the base unit, and it's abbreviated with a lowercase h. There's also deca, which is abbreviated DA to ensure that we don't confuse it with deci. Deca, which probably also reminds you of the word decade, is also involving the value 10, but now it's 10 times larger than the base unit, whereas deci was 10 times smaller. And finally, the last one you're likely to run into, even though there are many other prefixes out there, is mega, which is 1,000,000 times larger than the base unit. So when someone talks about a megagram, a megameter, a megaliter, or a megajoule, they're talking about a value that is 1,000,000 times larger than the base unit. These prefixes are important to know and to be comfortable working with, but again, depending on how you've seen them before, if at all, you might need a lot of prefixes to get comfortable using them. If you haven't seen these prefixes before, I recommend committing to memorizing just 1 or 2 of them a day. If you do that within the next week, you'll have most of the metric system memorized, and you'll find that it's not too stressful. Let's do some examples to give you some practice. Most human hearts weigh a little bit underneath a pound, or if we were to weigh them using the metric system, we might find out that a human heart weighs about 400 grams. To give you some practice working with the metric system, first notice that I've used the lowercase g to abbreviate grams. Now I'm going to ask you to change this value into another unit in the metric system. First, calculate how many kilograms there are in 400 grams. Remember, you can pause the video if you want to take a couple minutes to do this. Okay, so to determine how many kilograms are in 400 grams, I first have to remember that kilo means 1,000 times larger than the base unit. And anytime we change to a value that's larger than the base unit, I'm either going to move my decimal point to the left, or I'm going to divide by the number that's appropriate for the prefix. So there's 2 different ways to do this. One is to take the number 400, remember that kilo means 1,000 or 10 to the 3, so I'm either going to move my decimal point to the left 3 places, 1, 2, 3, and discover that 400 grams is equivalent to 0.4 kilograms. That's one possibility. The other possibility is to use division. Because a kilo is 1,000 times bigger than the base unit, I'm going to divide to do my conversion. So I can take 400 grams and I can divide it by 1,000. When I do this, I get the same answer, that there's 0.4 kilograms in 400 grams. Let's try another example. If a human heart weighs 400 grams, how many milligrams is this? Again, notice I'm using the abbreviation mg for milligrams, and note that it doesn't need to be confused with micrograms or megagrams because of the use of capitalization. Take a second to try this one. Feel free to pause the video. Okay, so how many milligrams are in 400 grams? A milligram is smaller than a gram, so I'll need a lot of milligrams to make up this gram measurement. Because it's smaller than the base unit, I can either move my decimal point to the right or I can multiply by the appropriate value. That appropriate value for milli is again 10 to the 3. It's related to kilo, but again in the other direction. So I have two options. I can take 400 grams and I can move the decimal point 3 places to the right. The decimal point is here, so 1, 2, 3. So 400 grams becomes 4, 1, 2, 3 kilograms, or 400,000 kilograms. Oh, sorry, milligrams. I mislabeled that. Let's erase that. So 400,000 milligrams in 400 grams. My other option is to multiply. Because there are 1,000 milligrams in a gram, I can say that 400 grams times 1,000 gives me the same answer, 400,000 milligrams. So in 400 grams, there's 400,000 milligrams. Now that we've looked in detail at the metric system, I'd like to step back for a second and just give you some perspective on using these metric units for measurements. If you've already grown comfortable using the metric system, this should just be a basic refresher for you. But if you've never worked with the metric system in a scientific setting or in your day-to-day life, one of the things that can be challenging about it is that we don't necessarily know how to visualize it. For instance, there are plenty of people in the United States that if you tell them you have a patient who weighs 180 pounds, they instantly can visualize what type of patient that might be. Whereas if you tell the same people that they have a patient that weighs 180 kilograms, now they don't know whether they're working with an obese adult patient or a pediatric patient. So to help aid you, if you're not familiar with the metric system, I'd like to give you a little bit of perspective on the base units. Let's start by looking at mass. The base unit for mass is the gram, and a gram is actually a very small unit of mass, relatively speaking. One way you can always check your own values and check yourself when answering in the metric system is to remember the fact that there are 5 cents in 5 grams. In other words, when a nickel rolls off the production presses at the U.S. Mint, it will weigh exactly 5 grams. This is helpful because if you're in a laboratory and someone asks you to go weigh 10 grams, you know you're going to measure a mass that's roughly equivalent to 2 nickels. Furthermore, it can give you some appreciation for how small the units we often work with in the health sciences are. Very commonly, patients are prescribed 50 milligrams or 250 milligrams. A milligram is 1,000 times smaller than a gram, so we're talking about very, very small units of measurement. For body weight, you'll often hear people referred to in terms of their weight in kilograms, and there's about 2.205 pounds in 1 kilogram. So a patient that weighs 220 pounds will weigh 100 kilograms, roughly. I don't expect you to memorize these relationships, but they can be helpful so that you kind of know how to visualize the numbers you see on paper. I mentioned previously when dealing with units of length that a meter, the base unit for length in the metric system, is very similar to a yard. And in fact, there are 1.09 yards in 1 meter. So in other words, a meter is just a little bit longer than a yard. If you're not in a scientific setting, you can usually describe them as being roughly approximate. If we go back to the example of a football field is 100 yards. Well, it's about 91 meters. So using yards and meters is an easy way to visualize exactly what distance we're talking about. For volume, this is one of the few things that most people are totally comfortable with, and for that we have to thank the soda bottle. A 2-liter soda bottle is exactly what the name implies. It's 2 of the metric base unit, the liter. So a 2-liter soda bottle is easy to visualize, and it'll help you understand what people mean when they say 1 liter, 2 liter, 3 liters, etc. Also, it's good to know about one of the other units that's often used in the metric system, which is the milliliter. A milliliter is 1,000 times smaller than a liter. But beyond that, it's also equivalent to the amount of liquid that can be held in a space that is exactly 1 centimeter by 1 centimeter by 1 centimeter. In other words, a cubic centimeter. So while previously many medical professionals used the term cc to describe the volume of medication in something like a syringe, increasingly you'll hear people use milliliters or even the abbreviation informally of mils. When someone says 50 cc's, they're saying 50 mils or 50 milliliters. So that's a nice one to remember in case you ever have to convert back and forth between the two. Just remember they're the same value. Beyond the base units that you're likely to see in your everyday life, I want to talk a little bit about the unit in the metric system for temperature. And that's because temperature is something that's measured differently by different people in different settings. There are 3 temperature scales that you're most likely to run into depending on the setting. Again, from the United States' most standard system of measurement, most of our temperatures are given in degrees Fahrenheit, which is abbreviated degree F. The F is always capitalized because this system was named after a German scientist named Daniel Gabriel Fahrenheit. Now, I want to compare this to 2 other temperature scales, and to do that, I'm going to use a theoretical thermometer and 3 points on this thermometer, which we'll compare across the scales. Since many people are taking this course as a health science prerequisite, in the middle of the scale, I want to put something that's easy to relate to, and that's human body temperature. To represent a number in the middle of the scale, we'll use body temperature, and then to represent sort of a relatively warm or hot temperature and a relatively cold temperature, let's go with something else we're familiar with, which is water and how water behaves. At the top of the scale, let's look at the boiling temperature for H2O, or the boiling point of water. And at the bottom, let's look at the point at which water freezes, or the freezing point of H2O. Now, in the Fahrenheit scale, how many of these do you know off the top of your head? For example, what is a typical average adult body temperature in degrees Fahrenheit? You probably answered right away, 98.6. This is kind of interesting because on any given day, there's very few adults that actually have a body temperature of 98.6, but it's kind of the accepted average. The freezing point of water is another one that you probably know off the top of your head because, especially here in Spokane, we use this for weather forecasts all the time. So when we say something's going below freezing, in other words, below the freezing point of water, we know that in Fahrenheit that's 32 degrees Fahrenheit. Do you know what the boiling temperature of water is in degrees Fahrenheit? Usually not everybody remembers this, but it's 212 degrees Fahrenheit. Here's the problem with this temperature scale. You're only used to these numbers, again, like most things in the United States standard system, because you've memorized them, and you hold them in your conscious mind so that you can use them when you need to. There's not actually any rhyme or reason to the Fahrenheit temperature scale, and in fact there's several competing theories about how Daniel Gabriel Fahrenheit came up with this scale in the first place. He invented it back in the early 1700s, and many people think that perhaps he went outside on a very cold night and mixed together some salt and ice and water and got the coldest temperature he could and called that 0 degrees. Other people believe that perhaps he set 100 degrees on the scale as his own body temperature, and maybe he was a little bit feverish when he was performing these experiments. All in all, it's an okay temperature scale in the sense that we're usually comfortable working with it, but it doesn't really have any scientific founding. And one of the problems with this is that it breaks down in a lot of situations, especially at very cold temperatures where we start to deal with negative numbers. Those can complicate our calculations drastically. You're probably familiar with the next temperature scale, which is the scale degrees Celsius, also called the centigrade scale, and it's represented with degree and then a capital C. Whether you call it the Celsius scale or the centigrade scale, this scale was named after a Swedish scientist named Anders Celsius, who also worked in the early 1700s. Anders Celsius made his own temperature scale, and it was actually later adjusted by Carl Linnaeus, who has been made famous as the man responsible for scientific naming in biology. Well, the problem with this scale is it's completely different from the Fahrenheit scale. Celsius's scale uses the boiling point of water and the freezing point of water and divides the temperatures in between into 100 different degrees. So the boiling point of water is set as 100 degrees Celsius, while the freezing point of water is 0 degrees Celsius. That puts human body temperature at about 37 degrees Celsius. Again, the issue with this is it's a fairly arbitrary way to make a temperature scale, and it's very common to run into negative numbers. So this makes scientists uncomfortable because it makes our calculations more difficult, and it's also a really arbitrary set of units. For this reason, in all scientific calculations, what you'll run into is the use of my third and final temperature scale, which is the Kelvin scale. Notice the Kelvin scale is not a degree scale, it's an absolute scale because it's fundamentally founded in one of the most basic truths about chemistry. Now the Kelvin scale, Kelvin is represented with a capital K, is based on the idea that all temperature is really just a measurement of how much molecules are moving. In other words, how much movement our matter has. And this goes back to what we talked about in one of our very first lectures when we said that cold substances, things like ice and solids, usually don't move around as much as warmer substances such as liquids or gases. The Kelvin scale uses the idea that if you took molecules and you slowed them down until they absolutely stopped moving, so they weren't even vibrating in place, that would be where there's no molecular motion, and that's what we would call absolute zero, because you can't go any lower. Once something stops moving, there's no way it can stop moving even more. Absolute zero is way down at the bottom of the temperature scale, and that's actually 0 Kelvin. It looks like you're writing OK because there's no degrees sign. Beyond that, the Kelvin scale is actually just the Celsius scale shifted downward. 0 Kelvin, or absolute zero, is actually at a temperature that's about 273 degrees Celsius below zero. Or it's at a temperature scale that's roughly 460 degrees Fahrenheit below zero. Very, very cold temperatures. But beyond that, each degree of the Celsius scale is equivalent to 1 Kelvin. So the freezing point of water in Kelvin is 273 Kelvin. The boiling point of water in Kelvin is also 100 units higher, just like it is in the Celsius scale, at 373 Kelvin. And this puts human body temperature somewhere around 310 Kelvin. The Kelvin scale is not something you'll run into in your day-to-day life. It's not a way that anyone's going to give you a patient's body temperature, but it is what's fundamentally at the base of all scientific measurements and calculations that involve temperature, and we'll be working with it a great deal. The nice thing is it's very easy to change between Fahrenheit, degrees Celsius, and Kelvin, and to do that you'll be given that sort of information and not expected to memorize it. We've looked at a lot of different units during this lecture. In particular, we've looked at the standard units that are used in the United States, the metric system with its variety of base units for length, for mass, and so on. And then we've looked at units for things like temperature. We've barely even touched on units that might be used to measure other qualities like energy, which is often measured in joules or calories. We'll come back to those later in the course, but for now you've seen that there are a lot of units out there. Before we start to talk about the numbers that are used in measurements, and not just the units, I want to point out that we will work with a lot of values that have complex units. And it's important to say that complex units doesn't mean complicated or hard to work with. It simply means a unit that has more than one measurement combined. And in fact, you're very comfortable working with these because when you drove somewhere at any point in your life, you had to look at a speed limit, which was actually a complex unit. For instance, in much of the United States, the speed limit is 60 miles per hour. Well, 60 miles per hour really is using two different units at once, the unit of miles and the units of hours. Often we abbreviate miles per hour as mph. What I want to show you is that when working with complex units in science, there's several different ways that they can be written out, and sometimes the way they're written makes them harder or easier to work with. For instance, if I write 60 miles per hour, it combines both the unit miles and hours into one abbreviation. And that can actually make things a little more difficult if I need to do something like convert the miles into kilometers or some other unit. For this reason, a lot of times I recommend writing out these complex units in individual pieces. Instead of writing miles per hour, you might write 60 miles / hours. That slash means divided by, or the word per. So 60 miles per hour is really 60 miles divided by 1 hour. And for that matter, you can even write it out as an entire fraction. 60 miles divided into 1 hour. Even though that's not as practical for simple applications, when you're working with calculations, you might find that this fraction form is easier to work with. There's plenty of other examples of complex units out there, whether they involve two units combined into one, like 60 miles per hour. The unit of density, for example, we looked at previously, might be something like 1.1 grams per milliliter. Or there's more complex units that can involve 2, 3, or even 4 different units combined into one. In the end, just remember that how they're written out is exactly how they were accomplished. 60 miles per hour was simply 60 miles over 1 hour.